Hello everyone, welcome back to our class. Let's continue study Chapter 8, Conduction. Section 3, Transient Heat Conduction Problem. Last several sections, we have learned several multi-dimension problems. We know multi-dimension problems generally is difficult to calculate to solve the equations. So this section we discuss transient heat conduction problem continuously. Three-dimension transient heat conduction. We will discuss three examples. One is generic lamp analysis. 2. Space effect and dimensionless transient equation. 3. Semi-infinite solid heat conduction problem. We will discuss three parts. 1. Generic lamp analysis. In the basic heat transfer, we have learned general length way to calculate some simple bodied heat transfer. But the method assumes there is only convection on the solid surface. There we only have convection on the surface, on the solid surface. But in fact, maybe there are other heat transfer modes on the solid surface. For example, convection, radiation, generation in the body. Maybe there is more factors. For example, here is a body. Maybe there is some heat transfer goes into the body. In the body, there is some generation. Also, in some surface of the body, there is some radiation and convection, include many terms. So, from the energy balance, we can establish one equation like this. The first term is the heat transfer from outside. For example, from this side, QZ from this surface ASH convection into the body. The second term is the generation in the body. The third term is Q convection, Q radiation. Two terms together is from this surface, radiation and convection together. The area is ASC. Maybe ASC and ASH is different. Finally, equals rho Vc dt over dt. Small t is time. This term is the internal energy increase. So the equation become more complex. More terms together. Our equation include radiation, convection, internal heat generation. Institute the heat transfer equation, we get Qs ASH heat flow in. Qg point means generation. V is volume. Minus h t minus th, t infinite minus t times t minus t infinite, convection. And epsilon sigma times t power force minus t surroundings power force is the radiation. Finally is rho Vc dt over dt. Here is the energy balance equation. We can find this energy balance equation become more terms. Obviously, this is a inhomogeneous equation, it is difficult to obtain the strict solutions. But we can simplify to solve it under special conditions. For example, when the radiation is the biggest term, is much larger than convection, the convection maybe is negligible. If there is no radiation from the outside and no internal source, the equation becomes simple. Epsilon sigma times T power force minus T surroundings power force times ASR equals minus rho Vc dt d over dt. This equation can be solved strictly by separation variables. This equation certainly we can solve. Okay, certainly obtained the solution, but the solution is still very, very difficult, very long. Here is solution. T equals rho Vc over 4 epsilon sigma AST T power third, many terms together, is the solution. If the total heat transfer coefficient of solid surface can be expressed as an equivalent heat transfer coefficient. Notice here, equivalent heat transfer coefficient is not only convection heat transfer coefficient, is equivalent. And the initial internal heat source is ignored. The equation expressed as like this equation. Here HEQ is equivalent coefficient. So this equation may be obtained the solution. In this case, we can obtain the equivalent Biot number. We order Biot number equals HEQ times LC over lambda. When Biot number is smaller than 0.1, we can use the lumped way to calculate, to obtain the solution. That's to say, we can use the condition to apply the generic lumped analysis. We can use this equation, this method to calculate the problem. To calculate other lumped case, generally it is very difficult. Certainly it's very difficult. We have learned multiple dimensions problem generally is very difficult to obtain the solution. But we can do numeric analysis using capital. Most of the case, we can use the capital to do some solution, to do some calculation. But here, please remember, Biot number when smaller than 0.1 is the condition to use lumped analysis. Okay, even if we can use the lumped analysis, it's still difficult to obtain the solution. So the second part we discuss, introduce space effect and dimensional transient equation. Firstly is space effect. Lambda analysis is simple, but need to satisfy the condition. I said Biot number smaller than 0.1 is the condition to use lambda analysis. When the condition is not satisfied, the condition, other solving methods must be considered. In this case, the internal temperature gradient is not negligible. Maybe there is very big gradient, temperature gradient. For a one-dimension problem, without internal source, the conduction equation is simplified like this: partial t power second over partial x power second equals 1 over alpha times dt over d small t. This case, alpha is heat diffusivity. Solving this equation needs one initial condition and two boundary conditions. So three conditions. One is initial condition, two boundary conditions. So like this, partial t partial x at x is 0 equals 0. And minus lambda partial t partial x when x is L equals h times t minus t infinite. Here's boundary conditions. The first boundary condition reflects the requirement of the center faces symmetry. Obviously, the temperature field inner the body is multi-parameter function like this. Certainly, we just discussed the solution. The solution, the properties, t is the function x, small t, capital T, t infinite, L, lambda, alpha, h. Many factors has influence on the temperature field. It is solved generally by numeric method. Generally, it's very difficult to obtain the solution. So for convenience, define a temperature difference is theta equals T minus T infinite. Divide maximum temperature difference is theta I equals Ti minus T infinite. As a dimensionless temperature, theta star I equals theta over theta I equals T minus T infinite over Ti minus T infinite. We obtained a dimensionless temperature, theta star. Theta star changes in the range of 0 to 1 in the range. The dimensionless spatial coordinate is dimensionless spatial coordinate. X star equals x over L. The dimensionless term is T star equals alpha T over L power second. We think this term, dimensionless term, is Fourier number, defined as alpha T over L power second. Fourier number. Okay, the one-dimensional unsteady heat conduction equation becomes like this: power second theta star over power x star power second equals partial theta star over partial Fourier number. Here is a unsteady heat conduction equation. This equation needs initial boundary conditions. In this case, the boundary conditions become theta star equals when the tau star is 0 equals 1. And the second boundary conditions, another boundary condition. So there are three conditions. 1, 2, 3. Three conditions. Finally, the function form of the dimensionless solution of the temperature field becomes only three variable function: x star, Fourier number, and Biot number is the theta star. So it becomes a function of just three variables. So just a look becomes simple. We can solve empirically where Fo equals alpha T over L power second can be considered as dimensionless term. we think it is a time, dimensionless time. It has important physical implications. It is relative size of the heat conduction and storage of a solid. This equation has strict solution for plate and radial system with convective boundary conditions and can be simplified approximate solutions. Certainly, it's still very difficult. For example, a one-dimensional plate has an initial temperature Ti and suddenly put it in a fluid with temperature T infinite, knowing the x star equals plus and minus 1, negative, positive, and negative 1, there are same convective boundary conditions, and it is symmetrical based on x star equals 0. The strict solution is certainly is still very, very long, very difficult to remember. Cn is the integral constant equals in these terms for different for n is different. Cn certainly we can calculate is by different case. Also, notice the Cn is the positive root of the flowing transcendental equation. Very, very special. Cn tangent Cn equals Biot number. The above problems can also be approximated when Fourier number larger than 0.2. The solution of the infinite series above can be approximated by the first term only, which is like this, different terms. So just look, the problem is simple, but the solution is still very complex. So here C1 and C1 can be obtained by checking the tables based on the size of the Biot number. So for different the Biot number, we obtained different the integration constant. For example, C1, C1 different. Here is most cases we can check the table to obtain some integration constant. Okay, the third section, the thermal conductivity of semi-infinite solids. As the figure, a semi-infinite solid has a known boundary condition in inner solid like this. Here is a semi-infinite solid. The boundary condition T when x reach infinite, T is different time, also equals Ti. Here is the boundary. When the x is very big, the temperature is Ti. Here is one boundary condition. This is also one-dimension problem. Satisfy an equation certainly is still like this. Generally, it's difficult to solve the equation directly. For convenience, we can do some change. Order it equals x over 4 alpha t power half power 0.5. To change as follows, like this. We can do some change to change for the equation, original equation like this. But we can do some change. Finally, we obtain this equation. Also, for partial t power second, partial x power second, partial t, we can do some change. We use it to replace replace x. So after we doing that, instituting about 3 partial differential equation into the heat conduction equation, we obtain this equation. From this equation, we can find only one variable, only it. Just look, the shape becomes simple. So you can always solve it. You just plug in the initial conditions and boundary conditions. So this equation we can solve it because only one variable. Okay, here we give some example. For example, for the first type of boundary conditions, the temperature of the known interface is Ts. For example, we understand the boundary condition is temperature. Just interface, the temperature is known. Also, when x is 0, the it equals 0 is one boundary condition. So T when it equals 0 equals Ts. With the second boundary condition and initial condition, when x is infinite and t equals 0, it is the equivalent of t it to the infinite equals ti. So here is another boundary condition. After transformation, the thermal conductivity equation and the initial and boundary conditions are independent of x and t. So the thermal conductivity equation can separate variable like this. We can do some change to solve. Once integral, we obtain the solution like this. And then you integrate and you get distribution of the temperature field. Finally, we obtain the temperature field like this. C1 and C2 is still the constant. U is a dummy variable. The integral constant can be obtained from the initial condition and boundary conditions. Finally, we obtain the temperature field temperature distribution like this. T1 minus Ts over Ti minus Ts equals like this. Here is the solution. In fact, our equation is a Gaussian function which can be found in table in mathematics books. So this equation sometimes we can obtain. Thank you very much.